Okay, anybody have any homework questions or anything like that for thermo? So we are talking about what we started last time was two simplified material models. The first one was assuming a material is incompressible. We're really only going to use that for liquids, although there probably are applications where you could use it for a solid. And so the meaning of incompressible is that the specific volume is constant, and everything else is derived from that. The second simplified material model is the ideal gas law, or ideal gas model. That's obviously for gases. And so this is what we're talking about right now. And really both of these you can think of as substitutes for tables. If you have a table for the material, you can get the same information from that. You just don't always have a table for your mixture of gas or your mixture of liquids. All right, so for an ideal gas, the model that you tend to use in chemistry is P times the true volume is equal to, the extrinsic volume is equal to N times the universal gas constant times the absolute temperature. So this is the universal gas constant. That holds for every gas, and that's equal to 8.314 joules per mole times Kelvin. And you can rewrite that as P times the molar specific volume is equal to universal gas constant times the temperature. Okay, but we're not using either of these actually. For us, we are going to redefine our gas constant. So our R, with no bar over it, is the universal gas constant divided by the molar mass. So this is the universal gas constant. This is the mass per mole. And you can get that from the periodic table. Not in this room, though. And then the capital R, the one that we're going to use, is a gas constant for your specific gas. And then based on that, our form of the ideal gas law is, well, it's just going to be equal to P times the specific volume. That's the specific volume per mass is equal to RT. So that's the one we're going to use. Why are we going to use that one? Because the three variables that we're dealing with here are all things you can find in tables. Okay, that's why that's more useful to us. Notice that, so what does this let you do? For a superheated vapor, a gas that's not at saturation, how many properties do you need to specify any other property? Right, you need two. So for a gas that's not at saturation, you need two properties to specify the other properties, to define the state. And it's the same here. If you know two of P, V, and T, you can calculate the third. If you assume an ideal gas, then the following things are true. The first one is, well, I'll put this down again. PV is equal to RT. The second one is that you can assume that internal energy, specific internal energy, is just a function of temperature. The pressure and volume don't affect it significantly. The third one is that the specific enthalpy is equal to U plus RT. And so, well, that's also, a function of temperature. The fourth one is that C sub V, that specific heat for constant volume, it simplifies to just du dt. And the fifth one, the final one, is that Cp, the constant pressure specific heat, is just equal to Cv plus R, that specific, that gas constant for the specific gas that you have. Okay, so this is all the stuff that is available to you for an ideal gas. And what does it take for a gas to be treated as ideal? The gas has to be far from, it has to have a pressure that's far below the critical pressure, and a temperature that's far, I guess, above zero. Okay, far above zero. Because if you have a temperature that's too low, and when I say zero, I'm talking about absolute zero. If you have a temperature that's too low, the particles aren't moving enough to keep themselves apart. They get close to each other and then they grab each other. Okay, and if you have a pressure that's too high, they get, even if they're moving fast, they get pushed close together and then they grab each other. An ideal gas is like you're ignoring them grabbing each other. Okay, let's do an example. So let's say that we have 1/2 kilogram of air that's in a tank with a fixed volume. And we add heat to it. We add energy through heat. And it goes from a temperature of 20 degrees Celsius. So T1 of 20 degrees Celsius and a pressure 1 of 1.01 times 10 to the 5th pascals. That's just standard atmospheric pressure. To a pressure P2 of 2.02 times 10 to the 5th. So the pressure doubles. What's the temperature at that second state? All right, well, we know we're going to use the ideal gas law. So we know we're going to have to come up with the gas constant for air. How are we going to get the gas constant for air? Air is mostly nitrogen, a little bit of oxygen. Let's call it 80-20 as a fraction, okay? So it's 80% N2, 20% O2. And so we have to know what the molar mass is for N2 gas and O2 gas. Nitrogen molar mass for just a single atom of nitrogen is 14, and that is grams per mole. That's just the atomic mass that you read right off the periodic table. And so that says that N2 gas has a molar mass of 28. Oxygen has a molar mass, according to the periodic table, of 16. And so O2 gas has a mass of 32 grams per mole. We have a universal gas constant. Okay, so now before I get into the other stuff, I've been doing all my calculations in SI units, and I'm going to keep doing that. So we have to convert this to SI units, right? So the molar mass for N2 gas, it's 28 grams per mole. SI units is kilograms. So this is 28 times 10 to the minus third kilograms per mole. And the mass of O2 gas is 32 times 10 to the minus third kilograms per mole. Okay, well, we have 80% nitrogen, 20% oxygen. And so the total mass per mole is going to be 0.80 times 28 times 10 to the minus third plus 0.20 times 32 times 10 to the minus third. And that is 28.8 times 10 to the minus third kilograms per mole. Okay, well, for air then, R, I said this is total. Let's call this air. So the molar mass of air is this. So the gas constant for air is 8.314 divided by 28.8 times 10 to the minus third. And you get 288.7. And the units are, what do we have here? That would be joules per kilogram Kelvin. Okay, so now we'll go to state one. What do we know and what don't we know about state one that we're going to use to calculate the temperature at state two? So we know the amount of air. But we don't know the volume of the tank, right? So we're going to use what we know about state one to calculate the specific volume of the gas. So at state one, we have a pressure of 1.01 times 10 to the fifth. We don't know the specific volume, and that's equal to 288.7 times the temperature. Be careful. You always have to use an absolute temperature scale when you're using the ideal gas law. We were at 20 degrees Celsius, so that's 293 Kelvin. That's 20 plus 273. And so the specific volume is 0.837 meters cubed per kilogram. Now we're going to state two. What do we know about the specific volume at state two? Do we know that? It's going to be the same, yeah. So V2 is equal to V1. There's the same amount of material. So specific volume 2 is equal to specific volume 1. So now we can say that the pressure at state 2, 2.02 times 10 to the 5th, times 0.837 is equal to 288.7 times T, T2. And so T2 is equal to 2.02 E5 times 0.837 divided by 288.7. And you get the T2 is 585.6 Kelvin.
If the temperature given to us in Celsius at the beginning, should we convert back to Celsius again?
I don't care about that. Either one's fine with me. And then, do we know how big the tank is? Well, we have, so what's the volume of the tank? The volume is equal to the specific volume times the mass. We were told that we have 0.5 kilogram of air. So this is equal to 0.837 times 0.5. And so you get 0.418 meters cubed. Okay, one thing that I want to point out before I go on is for an incompressible material, you can pretty much always feel good about using the specific heat to calculate the change in specific internal energy. So I don't know, this is just something to remember. For incompressible materials, remember that the specific heat was equal to the total derivative of du dt. Okay. You can use this to calculate the change in specific internal energy for a given change in temperature. You know, delta T. And the reason you can do that is that the specific heat doesn't change very much as the temperature changes. So that's because C is pretty constant as T changes. So you can just treat that like it's a number and integrate, okay? Then you get to pull the constant out of the integral. For ideal gases, you also know that CV is equal to the total derivative of du dt. Make sure I'm using the right one. But only use this to calculate delta U for very small temperature changes. And the reason for that is that CV for an ideal gas changes more with temperature than C does for a liquid, okay? That's because C sub V varies more with temperature than C does for a liquid. Okay, so if like on an assignment or a test or something, I give you a value for CV and I give you a small, a 4-degree temperature change, something like that, then you can use this relationship to calculate the change in internal energy, but don't do it over 100 degrees. Okay. All right, the next thing that we're doing, so that's really the end of property relationships. So the property relationships are the tables with linear interpolation, and then treating liquids as incompressible materials, and then treating gases as ideal gases, okay? And those will let you relate properties at a single state. Those all have to do with equations of state. You're not calculating what happens over a process. You're at a single state using these things to calculate one property from other properties. Now we're going on to control volume analysis. This is the first time we're looking at this. And we'll get back to this with later topics. For now, the only things that we're going to talk about are conservation of mass, that often you'll hear called mass balance equation. And second, the first law. So I'm going to start with a mass balance. So the basic equation is easy to understand. If you have, a material, some kind of vessel like this, and you have material coming in, and then you have some other place where material is going out. The change in mass that's in that vessel with respect to time, so m dot CV is the mass that's in that control volume that you're considering. That's equal to the rate that mass is going into the control volume minus the rate at which mass is coming out of the control volume. So let me define these. So dm dt for CV, this is the rate of change of mass inside the control volume. M dot in is the rate at which mass enters the control volume at the inlet, or if there's multiple inlets, at the inlets. And M dot out is the rate at which mass leaves the control volume at the exit or the exits. Okay, so this is the basic equation. One thing that is going to be useful so we'll use this pretty often. How can you calculate the mass coming in or leaving? Well, let's think of, so I'm going to think of this as kind of like a semi-solid sludge. Okay, think of like the Play-Doh Fun Factory. Is that what it was called? So the control volume is over here, and material is coming out of the control volume as an extruded kind of thing. You know what I'm talking about, the Play-Doh Fun Factory, where you press the thing down and it squirts out with a given cross section. Okay, so imagine that, and let's think of the length, and then let's think of the area of the extruded shape, the cross-sectional area. At a single instant, what's the mass of this piece that's being extruded here? So the extruded mass is the volume times the density, right? And that volume, I didn't write this down, but this is supposed to be the length L. That volume is the area times the length. And then density is 1 over the specific volume. So this is AL over V. And we're going to start using V for speed soon. So let me just write this as volume. But are you with me on that? That's the mass of that piece that's shown there. Okay. Well, in this formula, we don't want the mass of that piece. We want the rate at which mass is coming out of this. So let's take the time derivative of this mass, okay? So what we want is dm dt to fit into the mass balance equation. And so that's going to be d dt of that area times the length times divided by the specific volume. Well, do any of those things change in time? I mean, you're imagining that this is a snapshot as you're squirting this material out of this, extruding this material. That cross-sectional area doesn't change. The specific volume doesn't change, but the length is changing, right? And so we can rewrite this as A over specific volume times dl dt. And dl dt you can think of as the speed of material coming out of that opening. So the speed of the material passing through the inlet or the outlet, whatever that is, the exit. And so our final expression is that m dot is equal to A times the speed of the material. That's like an average speed of material going through either the inlet or the exit, divided by the specific volume. And remember that, we've been using a capital V for volume, but now in this application, we're using it for speed, for velocity. Often we're going to be dealing with problems where the volume you're looking at is in steady state. Anytime something's in steady state, you've heard this before, it means that the properties are constant. And so the mass in that control volume is a property. So if it ever says steady state, that says that dm dt in the control volume is 0.
So if solids wouldn't always be 0, or
If what?
because solids are compressible,
Well, if you're using, so a case where something isn't steady state, like imagine a tank with liquid flowing in and a gas coming out or something. If the mass of liquid inside the tank is changing, then it's not steady state. If the level of liquid in the tank is staying constant, then it's steady state. That's what that means.
So it's just saying the rate going in is the same as the rate.
That's right. Yep, and actually that's, so in that case, then you just have mi dot is equal to me dot. Okay, let's do an example. So if a tank can hold 20 kilograms of water, and let's say some is in there, and so let's say that it starts with 5 kilograms of water in it, and the rate of mass flow in is 2 kilograms per second. and the rate of water flow out is 1.5 kilograms per second. How long will it take until the tank fills? And let's do a part B also. So that's going to be the first part. For the second part, let's say the speed of the water coming in at the inlet is 10 meters per second. And the speed going out at the exit is 25 meters per second. What are the areas of the openings at the inlet and the exit? All right, well, so our equation says dm dt is equal to the mass coming in at the inlet minus the mass going out at the exit. So we have dm dt is equal to 0.5. And now we can integrate both sides. I'm going to think of it this way. dm for the control volume is equal to 0.5 dt. And then I'm going to integrate both of these. So at time equals, so for time, we're going to go from 0 to t. We're trying to figure out how long this is going to take. Okay? For the mass, at time 0, we have a mass of 5 kilograms. And at time t, when we're trying to calculate this elapsed time, we have a mass of 20. That's what the tank can hold. Okay? So this says m for the CV, evaluated from 5 to 20, is equal to 0.5 t. And so 15 is equal to 0.5 t. And so t is equal to 30. Okay, what are our units? Seconds, it is seconds. And so that just comes from the fact that our time units for the rates are in seconds. Any questions about that? Okay, so second, now we want to calculate the area of the inlet and the exit. So at the inlet, we know that m dot in was equal to 2. And that's equal to the area of the inlet times the speed that we're given, 10 meters per second. Divided by the specific volume. I said this was water, right? So we know that the density of water is 1,000 kilograms per cubic meter. And so that says that the specific volume of water is the reciprocal of that, so 0.001 meters cubed per kilogram. So 2 is equal to 10A divided by 0.001. And so A is 0.002 divided by 10, so 0.0002 meters squared. Same thing at the exit. M dot at the exit is equal to 1.5. That is going 25 meters per second. So this is equal to the area at the exit times 25 divided by 0.001. And so A out is equal to 0.0015 divided by 25 and that is 6 times 10 to the minus 5th meters squared. This is just something I want you to think about, but if you have, if this is the exit, or the inlet, but it's easier to draw the exit. And say this is a gas or a liquid that's flowing out. What does the profile of velocities look like for this fluid that's flowing out? Is it all the same? You know, that's kind of the question. It really would look like this. I mean, I've drawn this as a 3-dimensional thing, but the flow rate would be really slow near the, near the boundaries, near the walls, and it would be at its fastest in the center. So what does it even mean? I mean, right at the wall, you'd have 0 speed. The speeds of the fluid vary along the cross section. And so remember that V is the average speed. Of the fluid. Okay, so in order to use that formula, you'd have to know something about the profile of speeds. But in the problems we're going to do, that it's just going to be given to you as a speed, and you don't have to think about it any more than that.
Yeah.
Okay. Anybody have any questions?
Is that why when gas is like escaping a cannon, like around the edges, the gas kind of curls away the center?
I think probably that has to do with pressure, I would guess, that just the pressure is higher inside the gas, and so it's pushing the gas into the lower pressure air around it.
I think that is kind of, because it's kind of gas coming out, but you have to, so it's kind of slower on the sides.
Slower on the sides.
Like when you shoot a gun, it's the same thing, it kind of has like, you
Yeah.
have a little bit of.
Yeah,
stuff
maybe.
that comes out, and
Maybe.
You have like the middle. where
Yeah.
it's like-
It could be. The thing it relates to that I think of is like when you hear a report of like wind speed, you'll see something that says 15 miles an hour or something, gusts up to 20 miles an hour or whatever. But that's measured at whatever height.
Yeah.
That's not the wind speed that you feel down on the ground. If you're lying down on the ground, you basically have no wind because it's the no slip condition that says that the air really isn't moving at all right next to the boundary. But the higher you go, the higher that wind speed is.
Yeah.
Any other questions? Okay, that's all. So you guys already took your test, statics test Friday.
Fun.
Yeah, it'll be good. It'll be good for all of us, like eating broccoli.